Dive. Today we're looking at something pretty cutting edge.
We are. It's this intersection of classical and quantum computing, specifically for time series forecasting, which is, always a challenge.
Exactly. And we've got some research material here detailing a new approach called quantum RWKV,
Right, quantum RWKV. It aims to merge the efficiency we see in classical RWKV models.
which are already quite efficient.
Yeah, exactly. Merging that with the, let's say, potential power of quantum circuits.
So our mission today for this deep dive is to really get under the hood of quantum RWKV.
Figure out what the core innovation is, how it actually works.
And crucially, when it actually gives an advantage. Because it's not always better, right?
That's a key point from the research, yeah. It's task specific.
And we should stress this is based on some rigorous academic work we're looking at.
Definitely. Okay, so where should we start? To really get the innovation, maybe we need context.
Good idea. Let's set the stage. Before RWKV, the big thing in sequence models was transformers, right? From that 2017 paper, attention is all you need.
Absolutely. Transformers were revolutionary, especially for language. No question.
But they have that scaling issue, the self-attention mechanism,
Right, it scales quadratically with the length of the sequence and squared complexity.
which for really long time series data becomes a real bottleneck, just computationally too expensive.
Precisely. It limits how far you can push them with very long sequences. And that's where the classical RWKV model from 2023 came in as a different approach.
An attention-free architecture, that was the big selling point.
Yeah, it completely sidesteps attention. Instead, it relies on these two core ideas, time mixing and channel mixing.
Okay, can you unpack those a bit? Time mixing and channel mixing?
Sure. So time mixing is sort of like a recurrent mechanism. It's how the model looks back and processes information across different time steps, capturing those longer range dependencies.
Okay, handling the time aspect.
Exactly. And then channel mixing is more about processing the information within each time step. It's a feed-forward network operating on the features, the channels, at that specific point in time.
Got it. And the key outcome of this design?
Linear complexity. It scales linearly with sequence length, not quadratically.
That's a massive efficiency gain compared to transformers for long sequences.
A fundamental difference, yeah. Makes it much more suitable for certain tasks.
Okay, so that's the efficient classical foundation RWKV. Now, quantum RWKV builds on this. How does it bring quantum into the picture? Where's the quantum magic, so to speak?
Well, the innovation in quantum RWKV is quite specific. It doesn't overhaul the whole thing. It targets one part, the channel mixing module.
Ah, okay, so it leaves the time mixing alone and focuses just on the channel mixing.
That's right. And instead of just the standard classical feed-forward network for channel mixing,
Yeah,
it introduces this dual branch system.
dual branch. Interesting. Tell me more.
So one branch is still the classical MLP, the multi-layer perceptron, doing the normal channel mixing job.
Okay, familiar territory.
But the other branch runs in parallel, and that's a variational quantum circuit, a VQC.
Ah, I see. So for channel mixing, the information flows through both a classical path and a quantum path simultaneously.
Exactly. It's a hybrid approach right there in the channel mixing block.
So what's the hypothesis here? Why add this VQC? What extra capability is it supposed to bring to the table for time series?
The core idea, the hope, really, is that the VQC can capture certain kinds of complex nonlinear patterns in the data better than the classical MLP alone.
How so? What is it about quantum circuits?
Well, they operate in Hilbert space, which is this, exponentially large state space compared to classical bit.
A much bigger playground,
A
essentially.
much bigger playground, yeah. And they can use quantum phenomena like entanglement to create really complex correlations and transformations on the data, things that might be very hard or computationally expensive for a classical network to learn. This whole field of quantum machine learning, formally introduced around 2017, explores these kinds of ideas.
Okay, so the VQC is like a specialized processor aiming to tackle complex nonlinearities using quantum mechanics. How does it actually work inside quantum RWKV? The research mentions three stages: encoding, entanglement, measurement.
That's the flow, yeah. First, encoding, you need to get the classical data into the quantum circuit.
Right, how's that done?
Quantum RWKV uses something called angle embedding. Basically, the input values from the classical part determine the rotation angles for quantum gates, specifically Pauli X rotation gates applied to the qubits.
So the classical numbers become rotation angles, setting up the initial quantum state. Makes sense. What's next? Entanglement.
Right. After encoding, the qubits go through entangling layers. These use gates like Xiaol, arranged in this specific ladder pattern in their design,
And the purpose of the Xiaol gates?
to create entanglement between the qubits. This weaves correlations and dependencies into the quantum state, allowing for more complex processing.
Okay, creating intricate relationships within the quantum data.
Exactly. And crucially, the parameters of these entangling layers, the rotations within them, are trainable.
Ah, so the model learns the best way to entangle the qubits for the specific forecasting task.
Precisely. It optimizes the quantum processing during training.
Okay, encoded, entangled, then you need to get information out, measurement.
Yeah, measurement. You need to translate the final quantum state back into classical numbers the rest of the model can use.
How does QuantumRWKV do that?
It measures the expectation values of the Pauli operator for each qubit. This gives you a classical numerical output per qubit.
Expectation values, so like the average outcome if you measured many times?
Sort of, yeah. It gives a continuous value reflecting the qubit state along the z-axis. These values are then projected back, usually through a linear layer, to match the dimensions needed by the next classical part of the network.
Okay, encode, entangle, measure. A clear quantum processing pipeline within the channel mixing. Now, the paper mentions PennyLane and PyTorch. Why are they important here?
They're absolutely crucial for making this work practically. PennyLane is this amazing software library. Came out around 2018.
What does it do?
Its key feature is enabling automatic differentiation through hybrid quantum classical computations.
Meaning you can calculate gradients, even through the quantum circuit part.
Exactly, which is essential for training. You need those gradients to update the parameters, both classical and quantum.
And PyTorch.
PennyLane integrates seamlessly with PyTorch, which is, a standard deep learning framework. So you can build and train this whole complex hybrid quantum RWKV model end to end using familiar tools like backpropagation.
Wow, okay. Being able to train the quantum and classical parts together end to end, that really is a significant step, makes it feasible.
It really does. It moves it from a theoretical concept to something you can actually implement and test.
Which brings us to the big question. Does it actually work better? Does this quantum enhancement pay off in terms of forecasting accuracy? The researchers tested this on synthetic data, right?
They did a pretty comprehensive set of 10 synthetic time series tasks.
What kinds of tasks?
A real mix, things like linear ARMA processes, which are quite standard,
Okay.
but also chaotic systems like the Logistic Map, which are inherently unpredictable. Then oscillatory signals, things with sharp jumps, discontinuous functions, and even combinations of these.
So a broad stress test covering different kinds of temporal dynamics.
Exactly, designed to see where QuantumRWKV shines and where it maybe doesn't.
And what was the main finding? Where did QuantumRWKV show a clear advantage?
The key takeaway, according to the paper, is that QuantumRWKV performed significantly better on tasks that involved, and I'm quoting loosely here, smooth nonlinearity, chaotic dynamics, or noise-driven signals.
Smooth nonlinearity, chaos, noise. Okay, that's specific. Can you give us some numbers, like from their table 1, maybe MAE or MSE results?
Sure, let's take the chaotic logistic map task. The mean absolute error, MAE, for QuantumRWKV was about 0.317.
Okay.
For the purely classical RWKV, it was higher, around 0.354. And the mean square error, MSE, showed a similar gap, 0.134 for QuantumRWKV versus 0.192 for classical. The paper explicitly marks this quantum better.
So a noticeable improvement for that chaotic system. Any other examples?
Yeah, the noisy damped oscillator was another strong case. MAE for QuantumRWKV was just 0.044, whereas classical RWKV was way up at 0.102.
Wow, less than half the error.
A significant difference, yeah. Again, marked quantum better. So for you, the listener, if you're dealing with data that has this kind of complex, maybe unpredictable or noisy behavior, this suggests quantum RWKV might offer real gains.
Okay, clear empirical evidence for certain tasks. What's the theory behind why it's better in those cases? Why chaos and noise?
The researchers suggest a few reasons. One is that enhanced representational power from the VQC operating in Hilbert space, it can just model more complex functions.
The bigger playground idea again.
Right. Second, the ability to represent entangled states might be particularly well suited to capturing the intricate dependencies you find in chaotic systems.
Entanglement mapping to complex system dynamics. Interesting.
And third, maybe the probabilistic nature of quantum measurement inherently provides some robustness when dealing with noisy signals. It kind of averages things out in a useful way. This ties into broader research on the universal approximation capabilities of quantum models, too.
Okay, that provides a solid theoretical underpinning for the observed advantages, but it wasn't always better, as you mentioned. Where did the classical RWKV win?
The classical RWKV model came out on top for tasks that had sharp discontinuities or simple autoregressive structures.
Sharp discontinuities, like sudden jumps in the data.
Exactly. Things like piecewise functions or square waves. The continuous nature of the quantum operations in the VQC, as designed here, seems to struggle with those abrupt changes.
Can you give examples and numbers for that side?
Sure. For the piecewise regime task, QuantumRWKV had a pretty high MAE of over 20.
Okay.
Classical RWKV's MAE was much lower, around 11.8. Big difference. The MSE also reflected this. The paper flags it's made classical better.
Right.
Similar results for the square wave and sawtooth wave tasks. Classical RWKV performed better there too.
So for data with sharp breaks or very simple repeating patterns, the current quantum approach seems less effective. Why might that be?
The thinking is that the continuous rotations and evolutions in the quantum circuit just aren't naturally suited to modeling those hard edges, those discontinuous jumps.
Whereas classical networks,
Classical networks, especially those using activation functions like ReLU, rectified linear unit, are actually very good at approximating piecewise linear functions. They are sort of inherently built to handle those kinds of shapes better.
okay, that makes sense. It's about matching the tool to the nature of the problem. Very clear task-specific strengths and weaknesses emerging. Let's zoom out a bit. What's the broader academic significance of this work by Chen and Kuo?
Well, the authors themselves point out that this is really one of the first systematic comparisons between these kinds of hybrid quantum classical recurrent models and purely classical ones, specifically in the temporal domain for time series.
So it's early days, but important groundwork.
Exactly. Given how much interest there is in both making sequence models more efficient for long series and in exploring quantum machine learning, this study provides some really valuable first empirical benchmarks. It starts to map out where quantum might actually help in this specific area.
And the study does acknowledge limitations, right? Like the size of the quantum circuit used was quite small.
Yes, they used a VQC with only 4 qubits and 2 layers, which is, feasible on current quantum simulators or small devices, but quite limited in representational power compared to what might be possible in the future.
So what are the next steps? Where does the research go from here?
Obvious directions include scaling up, trying deeper circuits, more qubits as quantum hardware improves.
Right.
Also exploring different VQC designs, maybe integrating them differently within the RWKV structure. And of course, the big one, testing these hybrid models on large-scale real-world time series data. That's where the real proof will be.
The synthetic tasks are great for controlled comparison, but real-world data is the ultimate test.
Absolutely.
Now, you mentioned training these things. The paper briefly touches on challenges like barren plateaus. That sounds ominous. How does this research deal with that?
That's a really important challenge in training quantum neural networks, yeah. Barren plateaus are regions in the parameter space where the gradients become vanishingly small, making optimization incredibly difficult, especially for deep circuits.
So training just stalls.
Essentially, yeah. Now, in this study, by using a relatively shallow VQC 4 qubits, 2 layers, they likely mitigated the worst effects of barren plateaus. Shallower circuits are generally less prone to them.
Okay, so the small scale actually helped avoid that problem for now.
It likely did. Plus, their specific choices for encoding and entanglement structure and the overall training approach using PennyLane were probably made with gradient flow in mind. But it's definitely a key area for future research as people try to build larger, more complex quantum RWKV models, how to effectively train them without hitting those plateaus.
Right, a challenge to overcome as they scale up. Okay, so wrapping this up, what's the core takeaway message for our listener from this deep dive into quantum RWKV?
I think the main message is that quantum RWKV shows real promise, but it's a task-specific promise. It demonstrates a significant advantage for time series forecasting when dealing with complex continuous dynamics, think chaos, smooth nonlinearities, noise.
So it highlights a potential niche where quantum can genuinely augment classical methods.
Precisely. It's not presented as a universal replacement for classical models. For tasks with sharp discontinuities or simpler structures, classical RWKV in this study was actually better.
Which is an important finding in itself.
Very important. It tells us that the benefit of quantum integration isn't automatic. It depends heavily on the characteristics of the data you're trying to model. This work gives us valuable clues about where those benefits might lie in the temporal domain.
Really fascinating insights. So a final thought to leave our listener with. Considering how fast both classical AI and quantum computing are moving, what breakthroughs might be needed to bridge these current limitations? Maybe make models like quantum RWKV more broadly applicable or even more powerful in their niche? Perhaps you listening can think about where modeling really complex, noisy, continuous temporal data is absolutely critical in your field.
That's a great question to ponder. What comes next?
Indeed. Thank you for joining us on this deep dive.